Good morning, sixth graders. Today we are going to be investigating the question, how do heating and cooling affect gases? Now, we have already talked about how heating and cooling affect liquids, right? We talked about how the molecules move really fast and they move further apart and they move past each other in liquids. And then cooling them slows them down a little bit and they huddle together like penguins. And then in a solid, the same thing happens as far as them moving and vibrating rapidly and moving slightly further apart. But remember, in a solid, they stay in a line. They keep their structure. Otherwise, the solid object would turn into a blob, right? If you heat something up enough, it will liquefy and then those molecules will move past each other. But in a solid, for the most part, they're going to stay in a line. Now today we are going to talk about a gas. That's the third phase of matter that we're going to talk about. Okay, so if you want to do this lab at home, you certainly can. It's a pretty simple one. All you need is 2 plastic cups, one with hot water and one with cold water in it. A plastic bottle. I'm using an 8-ounce plastic bottle. You can use whatever plastic bottle you want, as long as it fits into the cup, kind of like this picture right here. And then some detergent solution on a plate or in a cup of some sort. And detergent solution just means some dish soap mixed with a little bit of water, okay? We're going to start out looking at a couple animations, okay? So this first one is of a basketball. Make this full screen. So the basketball is deflated, as you can see. It is on a scale, and it is measuring 576 grams. 576 grams. Now this guy is pumping up the basketball. So he's putting air inside the basketball. And this demonstration is to show that air is matter. Okay, so now that it's fully inflated, it is 581 grams. So that's 5 more grams in just air. The basketball is the same. It's just that it has more contents. It has more matter. That air weighs something. Okay? Another example of this is air duster, or compressed air in a bottle for like cleaning computers, right? So we're measuring this can of air duster. It's 135 grams. And then we're going to use some of that air duster, squirt the nozzle so that some of it comes out. And then he's measuring it again, and you'll notice that it weighs less, okay? So we took some of this mass out of the can by taking some of the air out of the can. All right? Now we're going to look at the particles of gas inside of a balloon. Right, it starts out saying the particles or atoms and molecules of a gas have very little attraction for one another. In a solid, they're really, really tightly packed. In liquids, they can move past each other, but they stay fairly close. And in a gas, they're kind of randomly spaced. They barely interact with each other. If they collide, they just bounce off each other. The particles of a gas are much farther apart than the particles in a liquid or a solid. So let's play this, and we'll zoom into the balloon. And you can see, look at them. They're just kind of crazy, bouncing all over the place. All right? It's a little bit different than what we have seen in a liquid and in a solid. They're very randomly arranged. They don't stick together. Like when we put water on a piece of wax paper, that water those molecules stuck together. And in gases, they don't. They just cruise around. All right? Let's go back to the lab. Okay, our first part of the lab, we are going to warm the air inside the bottle. Okay, so I've got a little plastic bottle here. And it appears to be empty, right? There's no liquid in it, but is it really empty? That's my question to you. Is it really empty? What's in here right now? Air. It's full of air, right? It's not full of liquid, it's full of a gas, okay? So we are going to dip the top of this bottle into some detergent, and I'll show you that. I'll make the screen really big. I'll show you that. And then we are going to submerge the bottom of the bottle into the warm water, and it's going to warm the overlying air in this bottle, okay? And then we will do the same thing. We'll take that bottle, the soap is still on top, and we'll put it in cold water, and then you can see what happens. All right, so I'll make this big screen here. All right, I will, on this little plate, I've got a little plate. So it says on the lab, use a cup for the detergent, but you can just use any surface. And this is just dish soap, and it is mixed with a little bit of water. So I'm making a little puddle here on my plate. And it's kind of like when you blow bubbles, you know, with the little bubble wand. You are dipping the top of this bottle onto the soap, and then you'll be able to see, just like if you looked at a bubble wand, you can see if there is soap that goes across the top, and there is here. Okay, I've got a cup of hot water here and a cup of cold water here, and I hope you can see this on the screen. Okay, so the little film of soap is across the top, and if I submerge this into the hot water, you can see that the bubble grows, right? You're going to take this with the bubble still on top and submerge it into the cold water. Oh, it popped. That's going to happen. That's okay. We just get some more. We're going to put it into hot water, and you'll see the bubble come up. And then we'll put it into cold water, and you'll see the bubble shrink. It's magical. Do it again. We go back and forth. There goes the bubble, really big, and then we make the bubble shrink. Isn't that amazing? Now all you have to ask for Christmas is soap and a bottle of water, and you can be entertained for hours. You could put wax paper and a dropper on that list too, because that was very entertaining for you. So in the hot water, we make a big bubble. Oh, it popped again. I'm recording this video on a weekend, so I'm up at my mom and dad's house. Mom, do you want to come and see an amazing experiment? Here she comes. She's going to be, even at the age of 70 something, she's also going to be amazed at this. I'm going to put some more detergent here. Okay, make bubble here, and then we put it in hot water, and we're warming the air, and a bubble forms. And then if we cool the air, the bubble goes away. Wow. And it grows. It goes away. What is happening to those air molecules inside this bottle to make that happen? What do you think? Pretty neato, huh?
Yeah.
Pretty neato. Gosh, science is fun. Okay, let's put this away and let's answer the questions on your lab sheet. Alrighty. It says, what did you observe? What happened to the film of the detergent? Hang on, I'm going to pause. Okay, I'm back. What happened to the film of detergent solution when you placed the bottle in hot water? Well, what happened? What happened when this was in hot water? What's happening here? And this is just, you don't even have to talk about it on a molecule level. Just tell me what happened. What's going on right here? And then what happened to the bubble when you placed it in cold water? It shrinks, right? So now we're going to explain it with atoms and molecules. First, we're going to watch a little animation of what we just did, okay? Put this on full screen. Heating and cooling gas in a bottle. Play this. A bottle here, putting it in hot water. They're signifying that this is hot because it's red You can see these molecules are going absolutely berserk. They're zooming all over the place. Okay, now we're putting it in cold water. What's happening to these molecules? They're still randomly spaced, but they are definitely slowing down and condensing. So kind of the same idea of what happens to molecules in a liquid and in a solid, but they're just arranged a little bit differently. Okay. So what caused the bubble to form when you placed the bottle in hot water? Be sure to write about the speed of the molecules inside the bubble and the force on the bubble from the outside air. Okay. Again, we'll go back here. It says the red arrows in the animation represent outside air pushing down on the bubble film. When the bottle is heated, the molecules inside the bottle move faster. The faster moving molecules inside the bottle push against the bubble film, and this push from the inside air overcome the push from the outside air, forming a bubble. When the bottle is cooled, the molecules inside the bottle move slower. The slower moving molecules inside the bottle push less hard against the bubble film, and the outside air overcomes and pushes the push from the inside air, forcing the bubble down. Okay, we see this again. So there's air everywhere, right? It's pushing down against this, pushing down against this. But these molecules are so powerful and have so much energy that they win. They're pushing against the outside air. And when we cool it, these slow down, have less energy, and the outside air pushes this back. Right? Why did the bubble get smaller when you push the bottle into cold water? And be sure to write about the speed of the molecules inside the bubble and the force on the bubble from the outside air. Okay, so answer those two questions. And again, if you need to rewind this video and look back at the video I just showed you, please do that. Okay, the last part here. I'm going to show you this animation of comparing solids, liquids, and gases. Okay, so here we've got in a solid, remember, these are all in a line. Molecules are still vibrating. In a liquid, they are moving, but they're moving past each other, right? Liquid takes on whatever shape of the container that it's in. I can pour this water into a cup that has a square bottom, and it's going to take on that shape. And in a gas, total randomness, right? All right, so draw the circles to represent the molecules in a solid, in a liquid, and in a gas. Because all three different substances are all the same temperature, draw the same number of motion lines near the circles for each substance. Under the box, write about the arrangement and motion of the molecules and the attractions the molecules have for one another. Okay, we know that there's pretty strong attractions here, right? They stay in a line. Liquids, they move past each other, and then we just saw what happens in a gas. All right, this last question is taking this concept and applying it to your life. So imagine for a second that you work at a party store during the summer. You are going to ride home with the owner of the store whose car has been sitting in the hot sun all day long. You guys know how hot a car can be in the summertime when the windows are up. The owner tells you that you can take home a bunch of balloons, but advises you not to blow the balloons up all the way. Explain why the owner's advice is wise. Be sure to discuss how heating affects the motion of the molecules in a gas. Okay, so you're going to go home with a bunch of balloons, and you're going to transport them inside your hot car. Why doesn't she want you to blow the balloons up all the way before you leave? Or think of what if you did? What if you blew them up as far as they would go and then sat in a hot car? Now, this is the same thing. Try this sometime. If you go get a balloon, especially now that it's cold. Okay, so say you go to the dollar store and you get one of those silvery Mylar balloons. When you walk outside with that balloon, you are going to think that you got ripped off because your balloon is going to deflate partially. You'll get it in the car and it's going to be all soft. And if you don't notice, or if you don't go back in and complain, or maybe you do, let's say you go back in and complain. You go in and you say, my balloon is deflating. And then the clerk will look at you and think that you're crazy because you'll look back at your balloon now that you're inside the store and what's happened to it. Think about that one. Alrighty. Finish this up, and again with this part here, if you don't have the ability to actually draw on your Google Doc, you can go ahead and make these boxes on just a regular piece of paper and draw it out and then take a picture and upload it with this assignment on Google Classroom. Okie dokie. I will talk to you soon.